Week 4, Recurrent Neural Networks, EE546, and we are going to talk about gated units, gated recurrent units this week. We had the introduction, we have prepared ourselves for this, and now we're going to get there. So this is what we have done so far. We talked about what is a sequence in the previous weeks. We have talked about what is the difference between a feed-forward neural network and a recurrent neural network. We have defined the vanilla RNN, that feedback connection, and what does it mean and what is the purpose of that feedback connection. We have talked about different types with respect to input and output connections. And we've talked about how to train RNNs. We have made the definition of backpropagation through time, the problems, what is truncation in time when you are training them. And we have talked about what is difficult, what is the difficulty in training them, because they are notorious. I mean, recurrent neural networks are notorious for their difficulty in training. We have just talked about vanishing gradients and exploding gradients, etc. And we have done a live coding session as well. So at this point, actually, you know how to study or play with simpler RNNs. And starting with this week, we are going to learn LSTM, which is a de facto standard. I mean, it's, well, you do not usually hear this on a AI course now these years. Actually, these years, everything about AI is changing, but actually LSTMs are kind of a de facto standard. They are being used everywhere. And we are going to talk about it today. Okay, so let's get back to the vanishing gradient problem. Let me just take my image from there. We've talked about this the previous week. In the RNNs, we had the same problem where we had the same problem that we had in deep convolutional neural networks. In deep convolutional neural networks, we had many layers. And as more layers are added to neural networks, actually in general, the gradients of the loss function approaches to zero for many reasons. And there are many mathematical studies that shows this, mathematically prove this, or mathematically make sense of the practical situation, which we always observe. When you make the depth deeper and deeper, it is hard to train that network, because during backpropagation, the gradients, when you go from the end of the network to the start of the network during backpropagation in the reverse sense, when you get backwards deeper and deeper towards the input, your gradients vanish and vanish. At some point, they are lost. So you cannot train the initial layers, and when you cannot train the initial layers, you cannot train the network. This was something we already knew from convolutional neural networks. I mean, this is not something we have discussed only previous week. We have discussed it the previous semester. You'll remember it, and there are solutions for it. The previous week, we have tried to find a solution to it with truncation in time, because backpropagation in recurrent neural networks on a single layer recurrent neural network, a single one, is done through time, because you are calling that network number of times the sequence length. So the sequence length is like the depth of the recurrent neural network. And when you're training it, you can use all the sequence data for a single sequence. However, you may truncate it. So you may use trunks of the sequence, and during backpropagation, you could just do the forward run using some length of trunks, and you could do the backward run using another length of trunks, or the same length, doesn't matter. And we've seen that this could be a solution for some cases. I mean, because when you're truncating and making that shorter, that length of training shorter, the backpropagation through time shorter, so the extent of the gradients vanishing will go, I mean, will be smaller, I mean, will be softer. However, there was a problem with this. We said that we were losing dependencies, because in a sequence, the information could be an element of the sequence which is farther than a previous part of this element of the sequence. And if you're truncating the sequence into small parts, maybe they are not fed to the network during training together. I mean, there is still knowledge when you just overlap trunks and feed them. Maybe you're feeding that information, but you are losing some part of the long-term dependencies. That's what logic tells us. So how can we solve this problem? We want to just feed all the sequence, and we still want to train the network. And how can we solve this? Actually, we've talked about a solution to this concept in convolutional neural networks. And I've just mentioned this in the previous week as well. And if you remember the previous semester, if you have taken convolutional neural networks, EE541 with us, and you'll remember that the solution, the first solution was proposed by a Chinese guy called Kai-Ming He. He was with Microsoft by then, now he is with Facebook. He's a very good scientist. And he came up with the idea of the residual networks. And in a residual network, instead of simple blocks of VGG or LXNet, in a simple block of VGG, you had the convolutional layer, the ReLU, max pooling, convolutional layer, ReLU, max pooling. Instead of this, so instead of that simple part, convolutional layer, ReLU, the structure had a convolutional layer, or the so-called weight layer, because it could be convolutional or it could be fully connected, doesn't matter, doesn't matter. You're providing a ReLU, then another convolution, then another ReLU, but in between the input and the final ReLU, we are making a skip connection. Maybe you remember skip connections from the UNet structure, again from the convolutional neural networks from the previous semester. It is just this input being fed to the output. So instead of this, imagine you don't have this part, you don't have this part. So just imagine we don't have this part. I'm just deleting this part for now. Instead of this part, if we had only this part, it is just f of x. So this function is like function f, and I'm getting the output. But with this connection, what I'm actually getting is f of x plus x, which is good. Why? We may look at this, actually we have done this analysis in the previous semester, but when we analyze why this is good, because we could make the analysis in two ways. Let's analyze it in the forward pass. In the forward pass, it is not f of x. I mean, imagine f of x is a rubbish function and it doesn't work. And you're passing x, at least you're not losing anything. So that layer is not providing you anything. And in the backward run, that's a gradient. That's where the gradients could pass without any problems. So this was the slide of the previous week. So slide of previous week. Let's get to this week's slide. So guys, before we get to it, let me, actually that's what we are doing right now. Let me talk about the history of it. I already did. I mean, I said that it's Kai-Ming He and he used in ResNet. So I was just talking about ResNet, so I passed this slide quickly as well. So he had this idea. And I was just saying, if we look at it, if we analyze it two ways, in the forward run, even the forward function is rubbish. You don't lose anything because the identity is being passed. It's just, it is like this layer does not exist. Or in the backward pass, even these gradients, if these blocks kill the gradients because the derivative of the loss with respect to these weights, for example, is 0, we have a connection. And in the gradient routing, this connection will just route the gradient as it is. So it is like a gradient highway. That was the idea. And actually his experiments, this figure is from the paper of Kai-Ming He from the ResNet paper. He just checks it. The first test was without the residual connection. So without the residual connection. When he made experiments, as the layers got deeper, when you had 20 layers, the loss was lower without the residual connections, okay? But when he had the residual connections, when he had the residual connections, he saw that this didn't have to be, it didn't have to be the case. And with this approach, actually, Kai-Ming He et al. Designed the deepest, very deep, ultra deep networks, like 100 layers or 200 layers, because they were never dead. So the gradients never vanished. So this was an idea to create that highway. So if you want to summarize this paper, the idea behind this paper, the idea of ResNet was each layer had to learn the representation from scratch, which is correct. You are learning this f of x from scratch. As the network gets deeper, it's harder to optimize this learning from scratch. So why not let some layers not learn? Because even if it is scratch, the identity mapping will follow. And actually that was it. So plain convolution block versus the residual convolution block provided only the identity mapping, nothing else. And the identity mapping helped us in two senses. In the forward sense, it provided, if it is scratch, just assume that that layer didn't exist. And in the backward run, if this layer is killing the gradient, so it won't stop the gradients. The gradients will flow from the highway. That's why it's called the gradient highway, guys. This is called the gradient flow, the gradient highway. It's like, so it's like when the traffic is congested at these points, you have the highway and it's never congested. That's the, why am I explaining the analogy? Whatever, so that's called the gradient highway. Okay, and frankly, guys, actually, this idea was inherited by Çankaya from the recurrent neural networks. So let's remember what was the case for the recurrent neural networks. Let's remember, so what does it have to do with recurrent neural networks? If you remember, recurrent neural networks, when unrolled in time, are just deep serial blocks where the sequence length is the depth. So if the sequence length is S, actually this is just an S deep network. I guess you have no problems with that. So when the S is very long, that's a problem. It's getting very long, and it's getting deeper and deeper. The gradients will get that. So why not find a solution to it? Why not find a solution to it? There could be a solution. So if we had an advanced RNN, recurrent neural network, which is not a vanilla RNN, with residual connections, this ResNet, like ResNet, may help. And this is the idea of the gated recurrent units. And frankly, I'm bringing you to the idea of this gated recurrent units with RNNs with these highways, actually backwards in time, because actually LSTM, when it was first found in 1997, the funny thing is, it was Çankaya who have applied the idea of this identity mapping from LSTMs to ResNet. So it is a bit funny that you have learned ResNet first, you have learned the identity mapping in ResNet first, but actually you're learning the origin right now. The origin was LSTM. And in LSTM, they had this idea. They didn't call it the identity mapping, but the idea was the same. If we could create a highway where the gradients passed whenever they needed to, maybe even the sequence was very long, which means the RNN unrolled in time during training, during backpropagation in time, through time, it gets deeper. With that highway, we could solve the vanishing gradients problem, because when it's getting deeper, it's usually the vanishing gradients problem, not the exploding gradients problem. So the vanishing gradients problems that RNNs suffer is also referred to as the short-term memory problem. Because if you can just not make this thing learn long-term dependencies, you are not giving a long-term memory to it. So it is like the guy in the movie Memento. He could only just remember short-term memories. So it's like you have lost your long-term memory ability. You could just remember like minutes. We could that was the idea. So simply because if a sequence is long enough, they'll have a hard time carrying that information backwards through time. So in training, they failed. So to overcome this, in 1997, a famous guy, Schmidt-Huber is like one of the gods of recurrent neural networks and deep learning, actually, and is a postdoc, Hochreiter, they're from Germany, you might have guessed. They're from Austria, actually. They have come up with this idea, the LSTM architecture. They have created a mechanism for that gradient highway. It was not simple as this, because this is very simple. I mean, it's simple and stupid, but it's very effective. But the first LSTM was more like a gated architecture. And actually, you're all, only the ones who have come from the computer science department, which They've taken ANN, haven't taken 541, which is convolutional neural networks. In the final week, I talk about LSTMs, and I talk about this mechanism. So most of you already know this. I'm just repeating my words for you, but it doesn't matter. You are going to learn it right now. So we are going to talk about the LSTM now. That mechanisms again. And I'm using the figures from this guy. Is a very famous guy. I mean, I don't know if he's famous, but the YouTube video he's prepared for this purpose has been watched many times. So I guess he's considered to be famous. So I'm going to be using his figures, but visit his blog. He talks about this mechanism and gated units very well, and visit his YouTube video as well, because he just prepared the YouTube video. It's fantastic. I mean, it's the best video that ever explains this mechanism. I'm going to be using his figures to explain this mechanism as well. So we'll start with LSTM, 1997, then continue with GRU. And frankly, there's something funny again. Although GRU is newer, which is the Chinese version of the LSTM, it is architecture-wise simpler. They tried to make a more efficient one compared to the original LSTM, but they are considered to be quite similar in architecture. LSTM, I mean, it is believed that LSTM is a bit more successful in performance, but GRU is slightly better in computation. We'll get there, don't worry about it. So once again, RNNs in a nutshell. RNN is a single network which is called once and once and once and once and over and over and over and over again for a sequence. So this is my sequence, I'm calling it. I'm feeding here the hidden state. So the first hidden state. So let me just call it A, for example. A0, traditional all zeros. So this is A1 being fed here, A2 being fed here. So it's just I'm feeding the network. You know this. So in RNN, while processing, we're passing the previous hidden state to the next hidden state. And this is actually the memory of the network. This was what we were proud of about RNNs. I mean, in the previous weeks of this course, when we were trying to describe the difference of recurrent neural networks compared to feed-forward neural networks, that was the feedback mechanism, the hidden states themselves, that created that memory. Okay, so it acted as the network's memory because it holded information from the previous sequences and it passed it, and that information being sent in a sequential manner created that so-called memory. Very good, very nice. So it was like we had the input and we had the previous hidden states combined, concatenated, and fed to a activation function, which was traditionally a tangent, tanh function, so hyperbolic tangent. And that was the next hidden state. And if you needed to create an output, you added something here, again, another layer, a dense layer, a connected linear layer, and you had the outputs. Or if you don't want to, maybe you just created a many to one architecture, you're connecting this to another one in which you're concatenating the outputs and go on. It went on like this. So, and the non-linearity was created by the hyperbolic tangent, the tanh function. Good. We know this. I mean, we have been talking about this for weeks now. Okay. RNNs, the reasons RNNs used traditionally this tanh function was because tanh function was bounded. It took values of any input, so from infinity, minus infinity to infinity. However, the output was bounded between -1 and 1. So it was like regularizing the output. So it was like the hidden states, the memory, never going crazy. The hidden states, the actual mathematical values, the hidden states were bounded within a region. So it was like it was telling the short-term memory, okay, keep your values around this region so that it will make sense, because it doesn't make sense if you just use values from -infinity to +infinity. It's difficult to regularize them. So it was like a regularizer for the hidden state values, this tanh function, and that was why it was traditionally chosen. Good. The problem unlike ResNet, there was no identity function. Because when you were training it, you did backpropagation through time. And if there was a problem with the weights here, because there were weights here, and if the derivative of the loss with respect to these weights were something like 0, you lost it, you're dead. Anything before that sequence, don't even try to train it because your gradient is dead. What if we had something like a highway combining the input to the output so that the hidden state could flow? That was the idea in LSTM. Actually, it is this. I mean, it doesn't look that way, but these are gates. These are gates that you can open and close, and they open and close according to the data. So unlike ResNet being so simple that the identity always flows to the next state, in this one, we have a mechanism to not update or to forget the hidden states. And for this purpose, there is a gating mechanism. When we say gates, I'm using the literature of computer engineering. You know, NAND gate, OR gate, AND gate, those gates using on logical values of 0 and 1s. So when you use gates, it's either 1 or 0, right? But these are like more fuzzy gates because I'm using a sigmoid function which is between 0 and 1. So the sigmoid, if it is 1, it's just allowing it to pass. If it is 0, it's not allowing it to pass, it's just killing it. Or if it is something in between, is allowing some of its energy to pass, kind of. So these are like gated units, gated mechanisms, but fuzzy gated mechanisms, because fuzzy logic, fuzzy gate means your logical values is not binary 0 and 1s. You're getting values between 0 and 1s. Okay, so LSTM has this mechanism. It is a control flow of like a recurrent neural network, because you have hidden states in the input and in the output given an input. Good. So as you propagate forward, providing new sequences, you're getting new hidden states, but there is more. So let's get to what is more. Similar to the so-called highway in the ResNet, there is a possibility of a highway depending on these gates. So how do those gates manipulate that flow? We're going to discuss that. But we now know that we have that possibility, because if this gate is 1, it's just flowing. It's just flowing here. And if something could be coming here, or maybe if this gate is 0, then nothing is flowing, coming here. We're going to get to the mechanisms, don't worry. So because think of the red ones as gates. So the gate being 0, you're multiplying the gate with 0. So nothing being added. If it is 1, this is flowing. So nothing added. So it is just being flown. So this is whatever this is. I'm going to talk about this. Just being added to here. So guys, instead of an identity function, there are gating mechanisms that control the flow, whether to keep the same information or forget the information. So when you're creating those keep forget operations, actually you are making it possible for the recurrent architecture to keep long-term dependencies as well. So because if you keep an information in the sequence long enough, then you're making a connection between the first word of the sentence to the last word of the sentence, even if the sentence is too long. Okay, so how does it work? Let's get there. The first thing we should understand about LSTMs is, we haven't discussed these many details. In the previous semester, the LSTMs, unlike the RNNs we have seen, have 2 types of hidden states. The first hidden states, as we know of, which is called the hidden state again. The second one is called the cell states, guys, cell states. These are the C, denoted by C. These are the cell states, okay? These are the cell states that are being transferred to the next one. So it is not the output, guys. You can create an output using the cell states or the hidden states of your, it doesn't matter. So the output is created out of this box. So LSTM is purely recurrent. So this is not the output. This is not the output. This is not, they are not the outputs. These are the states, because LSTMs, unlike recurrent neural network, the vanilla RNN, has 2 types of states, the cell state and the hidden state, both of them vectoral, And both of them just having some values, vector of. So I've just said that this vector is of length L, this vector is of length K. They can be different mathematically. However, in most implementations of LSTMs, including PyTorch, they are usually the same. However, the theoretical proposal of LSTM by Schmidt-Huber and Hochreiter, it can be different. However, in PyTorch, when you use the LSTM function, they are same because it's implemented that way. So they are just a bunch of vectors, just like hidden states. One of them is called the self state. The other one is called the hidden state. Good. So in addition to hidden states, we have the concept of self states. Hidden states of an LSTM are pretty much similar to the hidden states of an RNN because they can only keep short-term dependencies. Why? Because a hidden state is connected through so many gates. There's a great possibility that you're going to lose that information while backpropagating through time. So because there are so many gates between the hidden state and the previous hidden state and the next hidden state, it can only keep short-term dependencies. However, this is not the case for the self state. Self state is connected to the previous one on a highway where there are some gates, like bridges going up and down. So they could be kept, they could be forgotten, or they could be updated. So self states can change, can be forgotten, or can be forgotten means reset, or can be kept the same as the previous one. Similar to ResNet in terms of being kept, because that means that's the identity function. But also it can be forgotten. So we are giving the self state the mechanism to forget itself or just keep itself or update itself a bit maybe if it needs to. That's why self states correspond to the long-term memories, guys. So self state acts as a transport highway that we've talked about that transfers relative information all the way from the sequence chain. How long it is. I mean, however long it is, how much longer, whatever it is. As the cell state goes on its journey, because you're feeding so many sequences, the information gets added or removed or updated, or maybe it doesn't happen anything. It doesn't, maybe nothing changes. And it is being decided by these fuzzy logic gates that change between 0 and 1. Because, again, repeat, sigmoid function changes between 0 and 1. Very nice design like this, yeah. I mean, the first time I've seen Kaimin K's ResNet, I was really sorry because it looked like something that everybody could think of, but they're not. And that's the same for LSTM. If you just have enough experience on RNNs, if you, can go crazy with them, at some point you come up with this idea if you're smart enough, and apparently they were the guys who were smart enough. Good. So just like we said, cell states were designed to be the long-term memory of the LSTM, and hidden states were designed to be by Schmidt-Huber and Hochreiter the short-term memory of the LSTM. That's why this guy is called long, short-term memory. Long-term memory just indicating the cell states, and short-term memory indicating the hidden states. So the gates of an LSTM, as we just said, will create the mechanism to create that long-term memory via the cell states by keeping the information, forgetting the information, or slightly updating the information. Those are the three things that you can do. That's why we have three gate structures. Actually, this one is the first structure, this one is the second, and this one is the third, which we are going to cover one by one. So in order to understand how the gates of the LSTM function, we first remember 10H and sigmoid functions, and we just did them in the previous slides. So 10H was between -1 and 1, which means that you're regularizing the values of the cell state and the hidden state between 0 and 1. Good for you, so that they don't go crazy. And the sigmoid is actually the gates. It's not a regularizer. It's the fuzzy logic. So it's keeping you between 0 and 1, which are the gate values. Okay, it is either closed, 0, it is either open, or it is slightly open, something between 0 and 1. So when sigmoid squishes values between 0 and 1, that's helpful to you to create gates. So if we observe, for example, the first gate, which we call the forget gate, we're going to do it on the next slide. As we just said, if it is 0, which means I'm going to be just multiplying every single value of the cell state with zeros, which means you've forgotten your previous state, which means the network is making a decision like, I don't need any more information regarding the previous part of this sequence. So whatever I'm going to decide with this sequence, I'm going to be using the information from this point and on forward. If you can say that, imagine you're translating from English to French and you've come to the point where there's the dot is. I mean, that was the question in the previous semester's final. You remember this. And if this is the dot, well, most probably your LSTM network, if it is a translator, should just activate its forget mechanism so that everything will be 0. Remember, we've conventionally made the initial hidden state to be all zeros. Zeros. So when you make it, you're making it zeros. Good for you. We don't know still yet if it's going to be zeros because there are other gates here which could make an additive value here. So if it is both 0, it's going to be totally 0. So if they're both 0, the forget gate and the input gate, so input gate being a dot in the translation, well, that makes sense for a translator system, right? So depending on these gates, we forget or keep or update. So how do we do it? It's simple, guys. I mean, if you just derive the functions, actually, you already got it, the mechanism. And the only thing missing is you're going to go over the formulation and the formulas and try to understand it yourselves, which some of you have already done in the previous semester because you have just worked on some of the formulation. So the gates decides what's going to happen to the cell state. Values come up in 0 and 1 because it's a sigmoid. And when it's 0, since you are doing a multiplication, you may be killing or letting it flow. So if you look at the formula, actually you're at this point creating an intermediate cell state, which I call the C-cap. At this point, we don't see this intermediate point. Actually, this intermediate cell state will be important next week because we are going to be studying some variants of LSTMs. This is the first LSTM architecture. There are many LSTM architectures that can be used in with many different architectures. This LSTM architecture just lets this C-cap flow, but some other architectures just feed them here, like just feed them to this. Let me draw it in a way that I can later erase. So you could feed it here. So this is called the people LSTM, which we are going to talk about later. But we don't in the, let's call the regular LSTM, we don't do this. And at this point, we create an intermediate cell state. And the formulation is, just like the RNN, you concatenate the hidden state with the input, okay? Concatenate the hidden state with the input, which is this one and this one and this one. So this is the concatenation. So this gate applies some weights. These are the forget gates weights, and there's a bias, most probably. And you apply a sigmoid function, and you, as an output to that sigmoid function, you multiply it with the cell states. Guys, this is a vector as well, because this is a function. So this is something like n plus k by 1. And this is L, which is the length of the cells. It could be, L could be similar, equal to K, it doesn't matter. So L times K plus 1. So when you multiply this, this multiplication is L times 1. And this is L times 1 too. So you are feeding an L times 1 to the sigmoid. So the result of this sigmoid is something like, which is here, is something like 0, 0.5, 1, 0, 0.3, 0, 1 kind of something, which is of size L times 1. And you are, this is an element-wise multiplication, also called the header multiplication. You're element-wise multiplicating the cell state with this guy. So be careful, guys, when you are resetting or using the forget gate, you are not totally forgetting. Maybe you are forgetting some part of the state. That's also a possibility. I'm just forgetting this and this, and I'm just slightly forgetting this one, but I'm definitely not forgetting the elements, these elements of the cell state. So these are all vectoral. Always keep that in mind, okay? I've never mentioned this in the previous slides for the sake of simplicity, but that's the reality. And at this point, I have another vector which I called CCAP, an intermediate cell state. Some of the states forgotten, some of the states updated, and some of the states, because the sigmoid was 1 there, just left as they were. It's an updated cell state, which is going to be fed to the next gate of the LSTM, which is the input gate, which we are going to talk about in the next slide. Okay, we have time. So the gates outputs are vectoral, not scalar. So the updates on cell states are element-wise. Always remember this. Some aspects of the cell states are forgotten, some are kept, not all of them together. The things I've already said on the slides. Okay. Any questions, by the way? I'm just always, again, running so fast. Any questions? Good. Either it's Friday evening and you're so tired, or you get this very good, which I believe the second case, because this is the second time you're seeing this. Okay, so let's get to the input. Oh, let's give a break first. Let's meet in 10 minutes, 7:20. Okay, not 7:30, 7:20, and continue, okay?